Alright, I will have alluded to this in class, but the basic principle of statics is something that can be stated in a matter of just a handful of minutes, at most. And it is simply that the sum of all the forces acting on an object must be equal to 0, and it's the vector sum, and the sum of all the torques acting on an object must be equal to 0. When those conditions are met, you are in static equilibrium. That's about it. Okay, there is more to it. It gets infinitely difficult. Generally speaking, we put everything in the xy plane. And when we do that, we can break it down a little bit more into, oops, I used the wrong symbol here. I used delta where I went sums. Whew, it's right at the beginning of the video. I should probably just stop and re-record, but correction, this should be summation over and summation over and summation over. Alright. So the sum of forces in x would be 0, the sum of forces in y would be 0, and the sum of torques about the z-axis would be 0. And that's more the form we'll be using. So we're actually using a simplified set. We don't worry about sum of forces along z. We're treating it as though everything is happening in a singular plane of action. It makes things a little bit easier. Okay? Now, that's pretty much it. Technically, we've got all these things, and accelerations are 0, which normally accelerations being 0 just tells you that your velocities are constant. Really more in these problems, we're talking about the velocities are also in fact 0. But the most important point in all of this is that all the accelerations need to be 0, all the sums of forces need to be 0, all the sums of torques need to be 0. And yeah, that's it. That's the principle of statics. That's all we're going to be doing with this. So we're 2 minutes into a video. What are we going to do with the rest of it? Well, let me give you an example that we can use to see how this works a little bit. I'm going to keep the conditions up here for the time being, and I'm going to show you a classic problem. We're going to have a ladder resting against a wall. The ladder will have a length L and a mass M. There will be static friction with the ground, but no friction with the wall. If the coefficient of static friction with the ground is mu sub s, to what angle with the ground can the ladder be placed before it begins to slip? This is an absolute classic for statics. Alright, I would love to keep those equations up, but they're pretty easy to remember, and I need a lot of room for the diagram here. So, let's do this. We're going to make the ground a nice white color so it stands out, and we're going to make the ladder something that will stand out against that, so we'll put the ladder in green. We're looking for what angle we can get it to. It's on the smaller side rather than on the larger side before the whole thing begins to slip. Alright, let's decorate this with the forces. I should have said that this ladder is uniform. Why? Because that statement tells us where gravitation will act. Gravitation would therefore act from the center. Okay, what other forces would we get? Well, there are a couple obvious ones. There's going to be a normal with the ground. There's also going to be a normal force with the wall. And if we're looking at this, if we need this to be static, we need this bottom end not to slip. We need a force that's opposing that normal with the wall. The static friction with the ground is going to be the story there. So there are all of our forces. To get a little bit more information in here, if we come from the end here, then it's a distance L over 2 to reach the midpoint, and it is a distance L along the whole ladder. Okay, so those are all of our forces. We'll use them to generate the sum of forces and the sum of torques. So sum of forces along X. Well, we've got Fs going towards the right. We have the normal with the wall going towards the left, and it's all equal to 0. So that means the static friction force must be equal in size to the normal force with the wall. We'll come back to that. Alright, sum of forces in Y. Well, we've got the normal with the ground acting upward. We have gravitation acting downward. That's all equal to 0. That means normal with the ground must be equal to mg. Okay, those together give us an interesting condition. They mean that mu sub s times mg that's the largest friction can get, must be equal to the normal with the wall. That's all great. It seems like we've solved everything, except we haven't found the one thing we want. What angle can we twist this whole thing to before it comes falling down on us? That's going to require the sum of torques. In order to do the sum of torque part, we have to choose a center of rotation, though. Usually your choice of center of rotation should be done to reduce the number of torques you need to calculate or the number of unknowns that you have. In this case, I'm going to go with reducing the number of torques I need to think about, and I'm going to put the center of rotation at the base of the ladder. So now I don't need to find the torque by the friction force, and I don't need to find the torque by the normal with the ground. So that choice means I only have 2 other torques to worry about. Any other choice and you'd have at least 3. Alright, so let's see. Sum of torque. Well, we need to find the torque due to the weight of the ladder. And I'm going to use light blue for this. Lever arm model is very helpful here, because otherwise you end up thinking about R is coming out along here and your phi is the angle coming around, and you figure things out that way. But if you think about lever arm model, here's a line through that force. I just want a perpendicular distance to it. And that's pretty intuitive to see. It's L over 2 along the hypotenuse, and I want the adjacent. Let me see, is this going to be a positive torque or a negative one? This will be a negative one using right-hand rule. So we'll have minus. The distance is L over 2 cosine of theta times Rmg. Negative because it's clockwise. Alright, we now need to do the same thing coming out the other way. This is the one where it would get super annoying, because now you're trying to figure out this angle phi up here. Or maybe this one in here. But again, we can use lever arm model. There's our line through our force. There's our R perpendicular, and we can see it's the same as this side right here, which is the full length times the force. Or sorry, this would be NW. Okay. So now to find our answer, we're going to take the normal we found above and substitute it in. And from there, we should be able to find our angle. Now let me think and make sure I'm not making any mistakes here, because that's always a thing. And indeed, I have made a mistake. Alright, so let's fix that mistake. It's a fairly big one, and it happened right here before I substituted in even. This distance to go up is not L, it is L sine theta. Some of you may have been screaming at me there. So the correction, we get a sine theta here, and then our normal with the wall. That also causes a correction down here, where the missing sine theta is now inserted. USMG, that's fine. Okay, we are now good to go. All right, looking at this, L, M, and G are common to all the pieces. We can divide through by those and get rid of them entirely. So we have minus cosine theta over 2 plus, mu sub s sine theta equals 0. All right, cosine theta over 2, we'll move it to the 0 side and rearrange things a bit. Mu sub s sine theta. I'm going to divide by cosine on both sides. 1/2 is equal to mu sub s sine theta over cosine theta, which you can see that's going to become a tangent. We'll divide through by the mu sub s, and we'll find the limiting angle. Oops, I want to do theta equals. Will be based on 1 over 2 times mu sub s. So as a quick example, if mu sub s is equal to 0.5, then that would be inverse tangent of 1, and we'd get a 45-degree angle for the limiting case there. Any angle that is less than 45 would lead to falling. Oops. Okay. All right, that ran a little longer than I wanted. 10 whole minutes just to get through that, but good example. And hopefully it will help you out as you're trying to figure other things out. This is the whole process. You identify all the forces, you write out your sums of forces, then you figure out a center of rotation, you write out your torque equation, you use, you use the combination of all of the equations to find your answer. All right, so that is it for basics of static equilibrium. See you in the next video.